Hello, everyone, and welcome to another AP Chemistry virtual lesson. My name is Michael Fairbaugh, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. And we are going to talk today about Unit 3 in AP Chemistry, Intermolecular Forces and Properties. Just want to remind you that you can always go to apcentral.collegeboard.org to get more information about the support that the College Board is providing for schools that may be closed, as well as information about the AP exams. Make sure that you have access to scratch paper and a periodic table. Remember, at any time during the lesson, if you need to pause, feel free to do that. And let's go ahead and get started. Today in our lesson on Unit 3, we'll talk about intermolecular forces and properties of liquids and solids. And then I'll give you a brief comment about particle diagrams for solids, liquids, and gases. But the majority of our lesson will focus on intermolecular forces and how that affects the properties of liquids and solids. As far as the science practices, you can see here, explain the degree to which a model or representation describes the connection between particulate level properties and macroscopic properties. So again, this connection between the particulate level and macroscopic, so how the actual substance behaves, will be our focus. We will talk about the polarity of molecules today. So in earlier lessons, we talked about the polarity of bonds and the geometry of molecules. So we'll put those two concepts together. We'll definitely talk about the attractive forces in between molecules and particles and the properties of liquids and solids. For our warm-up problem today, the AP practice question from yesterday's lesson looks like this. We have a molecule, S2Cl2, that's 2 sulfurs and 2 chlorines. And in part 1 of this question, we have to complete the Lewis electron dot diagram for the molecule. So they've given us a skeleton, and we have to fill in all of the bonding pairs, which I will use as dashes, and non-bonding pairs, which I will use as dots. As far as how many valence electrons we have to work with, each sulfur has 6 valence electrons. Each chlorine has 7 valence electrons. So we have 2 of sulfur and 2 of chlorine. That would be 12 plus 14. So a total of 26 valence electrons. Let's start by connecting the atoms together. Each dash is worth 2 electrons. So 2, 4, 6. Now let's put the lone pairs of electrons around the atoms and see if we can get to 26. 8, 10, 12, 14, 16, 18, 20. 22, 24, 26. So unlike some of the molecules that I showed you in yesterday's lesson, which had to have double or triple bonds, we were able to satisfy all of the valence shells for each atoms with a complete octet, and we did not have to make any double bonds. The next part of the question asks, what is the approximate value of the chlorine sulfur-sulfur bond angle? Now, just because a molecule is drawn in a straight line does not necessarily mean that's the actual shape of the molecule. So some students, when they answered this question on the AP exam, they thought that the bond angle should be 180 degrees. Why? Because that's the way the molecule was drawn on the paper. Now, we know that if I have, in this case, a sulfur, and there is a chlorine on the one side, and there is a sulfur on the other side, and there are these lone pairs of electrons as well. This represents what is called sp3 hybridization, and there are 4 electron domains. So when you have sp3 hybridization and 4 electron domains, the bond angle should be 109.5. Now, it might be a little bit less than 109.5 because of the compression of the bond angles with those lone pairs, but the AP exam scoring guidelines accepted any value between 104 and 110 degrees. 180 degrees was not accepted in this case. All right, moving on to our next question. We have 2 Lewis electron dot structures for something called fulminic acid, hydrogen, carbon, nitrogen, and oxygen. They have already given us that the diagram on the left is the better representation. Justify your answer based on formal charges. Now, some students did not focus on formal charge. They would say things like the following. Well, carbon normally forms 4 bonds, and so therefore they thought that the structure on the left would be better because it has 4 bonds to carbon. You have to talk about formal charge because that's what the question is asking. So in this case, let's go ahead and assign formal charges to each atom in each structure. Well, the hydrogen has only 1 valence electron and has only 1 bond, so a formal charge of 0. The carbon has 4 valence electrons and has 4 bonds, formal charge of 0 as well. The nitrogen has 5 valence electrons, no non-bonding electrons, so there's no dots on the nitrogen, and it has 4 bonds, formal charge +1. And then finally, the oxygen, 6 valence electrons. There are 6 dots, so 6 non-bonding electrons and 1 bond, formal charge of -1. Okay, let's move on to the other structure. Well, hydrogen will be 0 again. Let's focus on the carbon. That's going to be 4 valence electrons. I see 2 dots, so 2 non-bonding electrons and 3 bonds. Formal charge -1. Nitrogen happens to be 5 minus 4. So we have a +1 like we had before. And then finally, this double bonded oxygen, it's going to be 6, 4 non-bonding electrons and 2 bonds. So that formal charge is 0. Now, we're not done yet, but we at least have satisfied the AP exam request to talk about formal charges. I'm now going to scratch out this information because it's the same in both structures. So nitrogen is +1 in both structures. Let's focus on the differences. So we have a carbon that has a formal charge of 0. We have an oxygen with a formal charge of -1. In the other structure, we have a carbon with a formal charge of -1 and an oxygen with a formal charge of 0. Now, we are not asked to make a prediction about which structure is better. They already said that the diagram on the left is better. And I gave you a big hint in yesterday's lesson. So what I said in terms of the guidelines for formal charge is that if it's not possible for each atom to have a formal charge of 0, the more favorable structure is one in which the negative formal charge, if there is one, is on the atom with the highest electronegativity value. So it's about the electronegativity of carbon versus oxygen. So as you look on the periodic table, you know that oxygen is further to the right on the periodic table. That makes oxygen more electronegative than carbon. So it is more favorable to put a negative charge on oxygen. Here are the official scoring guidelines for that question. So students earned 1 point for a correct assignment of formal charges in the diagrams, and they earned 1 point for the explanation talking about a negative formal charge on oxygen, which is more electronegative than carbon. So make sure that you read the question carefully and answer what is being asked. Our next practice question from yesterday's class had to do with another Lewis structure. I'm going to go ahead and count the Lewis electrons for this, or the valence electrons for this Lewis diagram. So hydrogen is 1, oxygen is 6, and we have 2 of them, and nitrogen is 5. So grand total would be 1 plus 12 plus 5, that's 18 valence electrons. Let's start connecting 2, 4, 6, and now we'll add lone pairs and see where we stop at 18. 8, 10, 12, 14, 16, 18. So I ran out of electrons and now I'm going to have to make a double bond. So I'll just go ahead and make a double bond here. This is one possible Lewis structure. Let me go ahead and assign formal charges, not because I have to, just because I feel like doing it. So I've got 6 minus 5. That would be a +1 for this particular oxygen right there. And I have 6 minus 7, so a -1. Now this question said nothing about formal charges. I was just curious to see what those formal charges were. You might have drawn the structure with the double bond in the other position. And if you had assigned formal charges to this one, you would have realized that this would be formal charges of 0 for those two oxygens. Does it matter which structure you draw? No. Either one of these structures would be acceptable because the specific instructions did not mention anything about formal charges. A valid Lewis structure is on the screen, and you've got two valid Lewis structures in this case. Now, as far as the hybridization of the nitrogen, we're focusing on this nitrogen or this nitrogen. You get the same answer either way. So we have a nitrogen with a double bond, and then we have a single bond, and we have a lone pair of electrons. If we count the electron domains, and we don't count this double bond twice, we have a total of 3 electron domains, and that corresponds to sp2 hybridization. All right, let's get into our lesson for today. We're talking about Unit 3, which is Intermolecular Forces. And the first thing I want to mention is the polarity of molecules. It's very important that you understand VSEPR, so valence shell electron pair repulsion theory and molecular geometry. So we have two molecules, carbon dioxide and water. And I'm showing you what are called bond dipoles. There's a little cross in the arrow indicating the positive end of the dipole, and the arrow is pointing toward the negative end. Now, how do I know which end to draw this dipole? It always tends to point toward the more electronegative atom. So I have a separation of charge. So a carbon-oxygen bond is a polar bond. Just because you have a polar bond does not necessarily mean you have a polar molecule. In this case, we have a nonpolar molecule for the carbon dioxide because the dipoles cancel out. With water, you might see a similar kind of plane of symmetry in the molecule, and therefore you might think that somehow there is a balance between the left half and the right half of the molecule. But no, in fact, when you add those dipoles together, they do not cancel each other out. So water is polar. Now be very careful. Do not say, if someone asks you on the AP exam, well, why is water polar? The answer is, as on the screen, because all of the bond dipoles within the molecule do not cancel out. It is not acceptable to say that the reason why water is polar is because it is bent. Just saying that it's bent indicates the molecular geometry, but does not explain what is going on with the bond dipoles, any more than you could say, for example, that the nonpolar molecule, carbon dioxide, well, why is it nonpolar? Because it is linear, is not a satisfactory answer either. So to kind of emphasize that particular point, take a look at this molecule. This is hydrogen cyanide. It is a linear molecule, and as you can see, it's not symmetrical. We have a hydrogen on one side, and carbon is more electronegative than hydrogen. And then we have nitrogen. These are different dipoles. They're actually not even in opposite directions. So my point here to emphasize is that the answer for why something is polar or nonpolar has to do with, are the bond dipoles going to cancel out or not? If they do cancel out, the molecule overall is nonpolar. If the bond dipoles do not cancel out, then it is a polar molecule. So again, because it's bent or because it's linear is not a sufficient explanation. Now, speaking of other molecules, besides linear, we have trigonoplanar, tetrahedral, square planar, trigonal bipyramidal, and octahedral. I'm going to give you examples of each of these shapes. So there's carbon dioxide. Here's some boron trifluoride, methane, CH4, xenon tetrafluoride, phosphorus pentafluoride, and sulfur hexafluoride. Since the terminal atoms are the same and the dipoles are arranged symmetrically around the central atom, the bond dipoles within each of these molecules are oriented in such a way that they cancel out. So each of these 6 molecules that I'm showing you is classified as nonpolar. Again, because of symmetry would not be a sufficient answer. Because the bond dipoles are oriented in such a way that they cancel out is a more complete explanation of why these molecules are nonpolar. Now, let's focus on linear, trigonal planar, and tetrahedral. Some students will tend to extrapolate what I just said on the previous slide and say anytime a molecule is linear, trigonal planar, or tetrahedral, it should be nonpolar. But watch what I'm doing on these shapes. Notice how I changed the color of one of those atoms. HCN is no longer a symmetrical molecule, and the dipoles do not cancel out. For trigonal planar, I have picked a molecule. This is phosgene, has a carbon, 2 chlorines, and an oxygen, no longer symmetrical like the boron trifluoride was on the previous slide. Tetrahedral, you have to have all 4 atoms the same in order for it to be nonpolar. So because I have 1 chlorine or 2 chlorines or 3 chlorines, that messes up the symmetry. So all of the following molecules that I'm showing you on this slide, the bond dipoles do not cancel out, so these are polar. Do you have to consider the shape? Yes, absolutely. Do you have to consider the actual atoms and the bond dipoles? Yes. So consider both geometry and the individual atoms involved in that molecule. Another potential misconception has to do with what I talked about yesterday. A Lewis structure does not necessarily indicate the molecular geometry. So a student will draw a molecule. I'm now going to draw a dipole from hydrogen to oxygen. And they might conclude that this is a non-polar molecule because the dipoles cancel out. Now we know that that molecule is actually bent. So therefore, a Lewis structure can give you a false sense of the actual structure of the molecule. In a similar way, I might draw dipoles and think that this NH3 molecule is non-polar. But is this trigonal planar? What does the presence of that lone pair actually do to the molecular geometry? It makes it trigonal pyramidal. This molecule is polar. So please, when you draw your Lewis structures, remember that even though you don't necessarily have to make them aesthetically pleasing with all the proper bond angles to get credit for a Lewis structure, if you're going from Lewis structure to polarity, your molecule should be envisioned in 3-dimensional space. Another misconception has to do with the tetrahedral geometry. These bond angles are not 90 degrees. It's part of a tetrahedron. So is this molecule polar? Absolutely. The corners of the tetrahedron occupy 4 spots. If we have 4 atoms that are not the same, it's going to be polar, whether it's 2 and 2 or 3 and 1. So pay attention to what these molecules actually look like. Each of these molecules is polar, and you have to consider molecular geometry. Now, I will say, as we finish this conversation and move on to intermolecular forces, one last thing about shapes. All of the molecules here would be considered polar because the bond dipoles do not cancel out. So geometry that's bent, trigonal pyramidal, seesaw, T-shaped, and square pyramidal, it doesn't matter what those atoms are. The asymmetry of that shape, that geometry, makes it polar. But again, because it's trigonal pyramidal is not a sufficient explanation, try to get in the habit of saying that the bond dipoles either do or do not cancel out. You can mention the geometry, and that's a great thing to do, but go on to talk about how the dipoles interact with each other. Okay, so I want to talk about intermolecular or interparticle forces. I have a sample of water molecules here, and we're going to go ahead and add some heat to these molecules. I'm going to try to boil the water. Take a look at the next particle diagram and tell me if you think this is what's happening when water boils. Hopefully you realize that that is not what's happening to water molecules, but some people think that that is what's going on because they think about you're breaking up the molecules. Now, to say that you're breaking up the molecules can be confusing. You are breaking the molecules apart from each other, but boiling water does not separate water into hydrogen atoms and oxygen atoms. Boiling water is a phase change that does not break covalent bonds. Now, you are breaking the water molecules apart, but they are still water molecules. Let's talk about when a covalent or molecular substance is heated and undergoes a phase change from a liquid to a gas. What type of attractive forces are broken? This is a very common misconception that we see year after year in AP chemistry. So I want to pay special attention to this distinction between intermolecular forces and intramolecular forces. Intermolecular forces are generally weak and exist in between molecules or particles. Intramolecular forces would be the forces of attraction that exist within a molecule, and they are much stronger. In intermolecular forces, the particles are relatively far apart. With intra, the particles are relatively close together. So for example, if I just draw a simple diatomic molecule, and then I draw another one, I could talk about the attractive force between these molecules. So when I say far apart, that's what I mean. But if I am talking about the attractive force within the molecule, the covalent bond that holds the atom together, that is much stronger than an intermolecular force. So here I have some water molecules. Intramolecular forces are these, the attractive forces that exist within the water molecule itself. On the other hand, intermolecular forces are the attractive forces that exist between the molecules. So make sure that you have a clear understanding of the difference between these things. Okay, let's talk about how we can tell the relative strength of the interparticle or intermolecular forces based on some data. You're looking at a data table with boiling point of 87 and 165. We don't know what these substances are. They're just labeled as 1 and 2. Let me give you a little more information. Substances 1 and 2 are two different elements located in group 18 on the periodic table, so the noble gases. Which substance, 1 or 2, has the stronger attractive forces between the particles, and how can you tell? Well, you don't have any information about the identity of the elements. We can't talk about polarity, electronegativity, Lewis electron dot structures. All we have are boiling points. So it should make sense to you that if you have to change a substance from a liquid to a gas, energy is required to convert a liquid into a gas. The stronger the attractive forces between the particles, the more energy is required to overcome these forces as the substance changes from a liquid to a gas. So I would argue that substance 2 has stronger attractive forces, even if I have no idea of the identity of substance 2. I'm going to go with the higher boiling point would be stronger attractive forces. I'm going to go ahead and tell you that substance 1 was argon and substance 2 is xenon. Now these are noble gases. They are not molecules, they're individual atoms. They're just individual atoms, so of course they are non-polar. But since you can have liquid versions of these elements, there must be some attractive force between the particles that would cause a gas to condense into a liquid. So how can we describe the attractive forces between atoms in a sample of a noble gas? Well, let's start with a particle diagram. Here I have an atom with a nucleus and an electron cloud. Now, this is electrons indicated by these little negative charges. So as the electrons are moving around, they are in this electron cloud. At some point, if I could take a snapshot of these electrons for just a moment, for just an instant, the electrons might not be distributed evenly. Okay, well, let's say that happens. Can you see in this diagram that there is a greater concentration of electrons on the right side as on the left side? That creates an instantaneous dipole, not a permanent dipole, but an instantaneous dipole. So in this instant, the electrons are not distributed evenly, and so we have a separation of charge. Well, what if this particular atom happens to be near another atom? Now the dipole in one particle can induce a separation of charge in a neighboring particle. So this instantaneous dipole in one atom can cause a neighboring atom to have an uneven distribution in its electron cloud. This is what we call London dispersion forces. So I'm going to explain a little bit more about London dispersion forces. We start with a gas, and now we're going to go ahead and take this gas and lower its temperature. In the gas phase, these particles do not experience any attractive forces. But what happens if the temperature of this sample is decreased? So as it slows down, the particles start moving closer together. Eventually, the particles begin to experience attractive forces. Now, with London dispersion forces, it's the interaction between particles or molecules as a result of these temporary or instantaneous dipoles. It's because of the distortion of the electron cloud. Now, the electrons, are in continuous motion. So we have what is called polarizability. Polarizability is the ease with which the charge distribution in electron cloud can be distorted. You can talk about this as an adjective as well. You can say that one molecule might be more polarizable than the other. How can you compare argon and xenon? Well, we have 18 electrons for argon and 54 electrons for xenon. So which, in your opinion, electron cloud is more likely to be distorted? Which electron cloud has greater polarizability? Now remember, we already have the boiling point data in front of us. So if xenon has stronger attractive forces, you cannot say because xenon is more polar or is more electronegative or simply that it's just larger or heavier. It's specifically about the electron cloud. That's what London dispersion forces are all about. So a larger electron cloud has greater polarizability and can be more easily distorted. The larger the electron cloud, the stronger the London dispersion forces are. Now I'm giving you more data. So here are 4 noble gases: neon, argon, krypton, and xenon. Take a look at that boiling point trend. Similarly, I have nonpolar substances such as fluorine, chlorine, bromine, and iodine. And I have methane, CH4, followed by silane and germane and stannane. These are all nonpolar tetrahedral molecules that have a central atom, carbon, silicon, germanium, tin. Notice that the electron clouds are increasing. So the larger the electron cloud is, the more polarizable it is. A larger electron cloud experiences stronger London dispersion forces. I will say that all molecules have and can experience London dispersion forces. While they are generally a weak force, since all molecules experience them, you can mention on any AP exam when they ask you, describe the intermolecular forces, London dispersion forces should be your answer, and possibly other things as well. Now, be very clear. While these atoms, in fact, xenon is heavier than neon, iodine as a molecule is heavier than fluorine, and tin tetrahydride is heavier than methane, do not say as your explanation that a molecule has stronger LDFs because it is heavier or because it has a larger mass. Talk about the larger electron cloud, and you can say words like polarizable or greater polarizability. All right, I now have a discussion of 2 molecules side by side, and we have 3 sets of them. So we have nitrogen versus carbon monoxide, and I'm going to go ahead and put the boiling points up here. We have propane, C3H6, versus acetonitrile, C2H3N. And then we have isobutane versus propanone or acetone. Now take a look at these molecules. They are roughly the same size in terms of electron cloud. Hopefully you can realize that the molecule on the left compared to the molecule on the right has a difference. And that difference is not just the boiling point, it is polarity. So the molecule on the right is polar, whereas the molecule on the left is nonpolar. Now, the isobutane is not perfectly symmetrical, but it is a hydrocarbon, so it is generally a nonpolar substance, the C4H10. All right, if that's the case, if the electron clouds are about the same size and you're talking about one polar and one nonpolar, the polar molecule, as you can see here with the higher boiling point data in front of you, tends to have stronger intermolecular forces. So, what exactly are the attractions between polar molecules? Well, the attraction between polar molecules are called dipole-dipole forces. It's whenever the partial positive end of one molecule is attracted to the partial negative end of a nearby molecule. Let me show you an example. Here we have HCl molecules in the gas phase, And I've shaded one end of the HCl molecule to indicate a higher electronegativity. So there is a partial negative charge on the chlorine and a partial positive charge on the hydrogen. If HCl molecules in the gas phase are cooled, they will eventually, if they're cooled low enough, condense to a liquid, and they will start to experience what we call dipole-dipole forces. Okay, I want to go back and talk about something that I mentioned, and I want to highlight it even more than I already did before, and that is this part right here. I was making a specific choice by the comparisons I gave you on this slide. Electron clouds were approximately the same size. So let me come to a very important student misconception. If you are given two different chemical formulas, and one molecule is polar and the other molecule is nonpolar, some students think that the polar molecule will always have stronger intermolecular forces, and that is not necessarily true. So, is it possible that a nonpolar molecule that only experiences what are called LDFs for short, London dispersion forces, will actually have a higher boiling point than a polar molecule that experiences both LDFs and dipole-dipole forces? And the answer is yes. And does the AP exam occasionally ask questions like that? Absolutely. So in this example, CCl4 is carbon tetrachloride. Tetrahedral, symmetrical, dipoles cancel out, nonpolar. HCl, simple, diatomic, two atoms and they're different, polar. Of course, CCl4 can only experience London dispersion forces because it's a nonpolar molecule, but HCl would experience both London dispersion forces and dipole-dipole forces. Now we come to the most important part, and that's the data. It turns out that at room temperature, which is about 25 degrees Celsius or 298 Kelvin, carbon tetrachloride is a liquid. Whereas hydrogen chloride, I'm not talking about hydrochloric acid, I'm talking about the pure molecules of hydrogen chloride, it's a gas. So what temperature does CCl4 boil at? About 77 Celsius or 350 Kelvin. At what temperature does HCl become a liquid? Well, you'd have to cool it down to around minus 85 degrees Celsius. But here's the misconception. Students only focus on this, and they somehow think that HCl must have stronger attractive forces because it is polar. Let me show you the electron clouds. Here's a space-filling model of carbon tetrachloride, and here's a space-filling model of HCl. The CCl4 obviously has stronger forces. We can see that because of the boiling point data. So those London forces must be significant because of the large electron cloud. If you are given data in an AP question, you must consider the data. So here's an example. That exact question from the 2017 AP Chemistry Free Response exam. Portion of the exam. This is number 1, part D, and it says that there was a mixture of CCl4 and HCl, and it was cooled to 70 degrees, at which temperature the CCl4 condenses while the HCl remains in the gaseous state. Well, let's identify all of the IMFs in HCl. You should mention LDFs, so London dispersion forces, and dipole-dipole forces, because it's a polar molecule. What can be inferred about the relative strength of the intermolecular forces? So many students ignored the data and said that HCl had stronger forces. But clearly, if at this temperature, CCl4 condenses into a liquid, while HCl remains a gas, it is the carbon tetrachloride that has stronger intermolecular forces than the hydrogen chloride. So you have to go with the data. I will go ahead and put up the official scoring guidelines for this question. So 1 point for identifying all of the intermolecular forces in HCl, and 1 point for a valid justification in terms of stronger intermolecular forces because the CCl4 condenses at a higher temperature than HCl. All right. I'm now going to talk about another type of attractive force. We've talked about London dispersion forces and dipole-dipole forces. All right, on this data table, we have boiling point on the y-axis and molar mass on the x-axis. I don't let molar mass become a justification. It's simply just a property of these substances. There are 4 dots on the graph, and these 4 dots correspond to the boiling points of CH4, SiH4, Ge, germanium H4, and then Sn, tin H4. So are we talking about dipole-dipole forces here? No. These are all nonpolar molecules, larger electron cloud, stronger LDFs. All right, well, now we come to NH3, PH3, arsenic, and antimony with H3. I'm going to start with the antimony, SbH3. Arsenic has a smaller electron cloud, lower boiling point. Phosphorus has a smaller electron cloud, lower boiling point. Now, nitrogen has an even smaller electron cloud. Therefore, you would predict, based on this trend, that the boiling point of NH3 would be around maybe 150 Kelvin. But in fact, it's much higher. So we'll talk about that in just a moment. Here we have H2O, H2S, H2Se, selenium, and H2Te, tellurium. Let me start with the tellurium hydride. Now, selenium has a smaller electron cloud, so weaker London dispersion forces. Sulfur has a smaller electron cloud. You would predict, if we kept going in this trend, that since oxygen has an even smaller electron cloud, that the boiling point of water might be around 200 Kelvin. In fact, it is also much higher. So we'll talk about that in just a second. And here we have HF, HCl, HBr, and HI. Let me start with the HI. Bromine has a smaller electron cloud. Chlorine has a smaller electron cloud. And then finally, you would predict that fluorine might also follow that trend and have a boiling point of around maybe 175 Kelvin. But all 3 of these molecules, H2O, HF, and NH3, have higher boiling points than one might predict based on the trend in simply London dispersion forces. So what do these 3 atoms have that's special? Well, what they have that's special is they have a rather small size and they have a rather high electronegativity value. So based on that information, we have a special kind of attraction that has a different name. This is called a hydrogen bonding attraction. It is a strong dipole-dipole interaction which occurs between a small hydrogen atom that is bonded to either N, O, or F on one molecule, and then that attraction between another molecule. So it is to the nitrogen, oxygen, or fluorine on another molecule. Now, if we have a protein, which is a huge biomolecule, or if we have a sample of DNA, it is possible to have hydrogen bonding within a large biomolecule, like different strands of DNA or different sections of a protein between the amino acids. So you can have hydrogen bonding within a rather large molecule. But with small molecules like the ones on the screen, I'm showing a connection from the nitrogen of one molecule to the hydrogen on the other, and then the same with oxygen and fluorine. Now, watch out for the fact that I have CH3OH. Take a look at the fact that you have 1, 2, 3, 4 hydrogens. So another common student misconception is all I have to do is connect an oxygen on one molecule to a hydrogen on a neighboring molecule. So look for a moment at this particular dashed line that I have drawn. Read the information on the slide. And is this a satisfactory hydrogen bonding interaction? Well, hopefully by my tone of voice and the big red X on the screen, you can see that that would be incorrect, because the hydrogen that you are reaching out with this particular connection must be, as it says, directly bonded to either a nitrogen, oxygen, or fluorine. So this hydrogen is bonded to a carbon, so therefore that is not an example of a hydrogen bonding interaction. Okay. One more thing I want to talk about, which is not exactly intermolecular, but interparticle, is the attractive force between an ion and a polar molecule. So I can't really call this intermolecular because an ion is not a molecule. You may recall a couple of lessons ago, we talked about Coulomb's law, and there was an AP practice question involving comparing the attractive force between an iron cation and a polar water molecule. That's essentially an ion dipole force. So the attractive force between an ion and a polar molecule. Water is often the example. So I'm putting some water molecules around this cation, and I'm putting some water molecules around this anion. Look closely at the way I have oriented these water molecules. The negative end of the water molecule is going to be the oxygen, and the positive end of the water molecule is the hydrogen. So they tend to orient with a specific directionality, the ion dipole force. So pay attention to that if you have to draw a particle diagram, the orientation of the water molecule so that the opposite charges are attracted. Okay, so now I'm going to talk about properties of liquids and solids. Here we have two liquids, C5H12 and H2O. The boiling point of each liquid is listed. I'd like to talk about a property of a liquid which is known as vapor pressure. So what exactly is vapor pressure? It is the pressure exerted by a gas in equilibrium with its liquid phase at a given temperature. Now, to model vapor pressure, I'm going to go ahead and put some dots above the surface of the water in this flask. I'm at 300 Kelvin. What's going to happen to the number of dots in my particle diagram if I raise the temperature of this liquid? Well, let's do it and find out. 310, 320, 330. I'm raising the temperature of the water. So as you can see, what's happening to the vapor pressure, it is increasing. Well, why is that? Why is warming a liquid going to raise the vapor pressure? I have an answer for that. This is a diagram of number of molecules on the y-axis and kinetic energy of the molecules on the x-axis. Now, there are different kinetic energy values for any given sample of material, gas, liquid, solid. There's a kinetic energy, which is related to the temperature. Each molecule is not traveling at the same speed. Each molecule does not have the same kinetic energy. So because there is an average, we are looking at a Maxwell-Boltzmann distribution of kinetic energies for a sample of matter. I'm now just going to go ahead and draw a line on this diagram. Now this represents what it would take to get out of the liquid phase and into the gas phase. So all the molecules are not going to evaporate at once. In fact, look at the shaded portion of this graph. Only these molecules in that shaded portion have the required kinetic energy to escape the liquid. What would happen if I raise the temperature of the sample of matter? Well, I have drawn another curve in a different color. This curve is in red. So as you raise the temperature, you increase the average kinetic energy, and you also broaden out that curve a little bit. So it broadens the distribution. There's a wider distribution of energies available. And as you can see here, because of this shift in energy, there is a greater fraction of molecules that have the kinetic energy needed to escape. So now with a greater fraction of molecules that can escape, the vapor pressure above the liquid increases. Now, when you raise the temperature of a liquid, vapor pressure increases, and I'm showing you a curve with vapor pressure on the y-axis and temperature on the x-axis. If I go along the y-axis at 1 atmosphere, and then I intersect the curve and see what temperature that is along the x-axis, this would be the normal boiling point at 1 atmosphere pressure. There are ways of changing the boiling point of a liquid with different pressures, but for this purpose, I just want to kind of focus on that 373 is the normal boiling point of water. I have not drawn the curve for C5H12, which is called pentane, but I want to go ahead and ask you a conceptual question about vapor pressure. If you are given the boiling point of each liquid, which liquid has a higher vapor pressure? So based on the difference in boiling point, take a moment to think about which liquid should have a higher vapor pressure. If you want, you can stop the video, you can draw these flasks on your paper, and you can draw a certain number of dots above the liquid. Whichever flask you draw more dots in should be the flask that has a higher vapor pressure. So if you want to pause the video and take a moment and draw a different number of dots in each flask to represent the different vapor pressure, go ahead and do that. All right, well, if you did take a moment to draw a diagram, I'm hoping that your diagrams looked something like this. So what I'm showing you is because C5H12 has a lower boiling point, it has a higher vapor pressure. So I'm going to draw the curve. I'm going to draw the vertical line intersecting the x-axis at around 310 Kelvin. So you can see that we have a higher vapor pressure, and that's why it comes to a boil more quickly or at a lower temperature. So conceptually, make sure you understand all three of these concepts. Compare the intermolecular forces, compare the vapor pressure, and compare the boiling point for these two liquids. If all you have is the diagram that I'm showing you, hopefully you can see that the diagram on the left represents weaker intermolecular forces because it evaporates more easily. The diagram on the left would have a higher vapor pressure and a lower boiling point. So these are concepts that students sometimes confuse, especially vapor pressure and boiling point. As you can see, they are inversely related. So pay close attention to that distinction. I'm going to do a brief summary of particle diagrams and talk about bonding. We have 4 types of bonds I want to talk about with respect to the properties of solids. You've already seen this diagram before in an earlier lesson. So properties of an ionic solid. Relatively high melting point because of the strong attractive forces. So here are some examples of melting points, and they're all about 900 to 1,000 degrees or more. They are hard and brittle. And what makes them brittle is because if a stress is applied and the layers of ions shift slightly, now you have repulsion between ions of like charges. So an ionic solid tends to flake apart into crystals, or it's cleaved along well-defined planes because of that. And I think I mentioned in an earlier lesson that for an ionic material, it only conducts electricity when it's either melted or dissolved in water, because the ions are free to move around. In the solid state, it is not a conductor of electricity because the ions are unable to move around. Properties of a metallic solid. We talked about how they are good conductors of electricity because of the mobile valence electrons. So it has a SEA of delocalized mobile valence electrons. As far as it being brittle, it's actually not brittle. Metals tend to be rather malleable. So if you apply stress, it tends to sort of mold and reform and flatten. You can flatten them into sheets and draw them into wires because the metal cores can easily rearrange their structures within that metallic bonding model. And I mentioned in an earlier lesson that you can have alloys, either substitutional or interstitial. And especially with interstitial, you can see that the hardness changes. So steel is actually harder than iron because the carbon atoms, as they fill in the spaces, make it more difficult for the iron atoms to slide past each other. Okay, so ionic, metallic, covalent network is another type of solid. Here we have a big network of atoms that are all covalently bonded in this large 3-dimensional network. So 2 examples are diamond and quartz. Another example is silicon carbide. They have many strong covalent bonds, so very hard and rather high melting points because it takes a lot of energy to break all those covalent bonds. And then another example of a solid is covalent molecular. As I talked about, we have these relatively weak intermolecular forces. So they are characterized by relatively low melting points, and they are not conductors of electricity because their valence electrons are held tightly within the covalent bonds of each molecule. So sugar and water are covalent and they do not conduct electricity. All right, just a comment about particle diagrams, and then we'll look at an AP practice and your homework. Solids are close together. Liquids are close together in terms of the particles, and gases are far apart. So I've talked about how the motion of the solid particles is limited to vibration within the crystal structure. With liquids, they are constantly moving and colliding, and they tend to be very close together, and their properties are related to the relative strength of the intermolecular attractive forces. With gases, there are minimal or zero intermolecular attractive forces, and we can describe a gas in terms of the amount of gas, pressure, volume, and temperature. So on Monday, Mr. Byrne will talk about ideal gases and the ideal gas law, so more information about gases in the next lesson. Okay, so before I get to your homework, another example of please watch out for student misconceptions. This is from the 2018 free response, number 4, part A. You are given a table. Take a look at this table for a moment and you notice that CS2 has a boiling point of 319. COS has a boiling point of 223. CS2 is nonpolar because of the symmetry and the dipoles cancel out. COS is polar because you don't have the same symmetry and the dipoles do not cancel out. So another example of a nonpolar molecule that actually, because of its larger electron cloud, has stronger attractive forces. How can we tell? Because it has a higher boiling point. In terms of the types and relative strengths of all the intermolecular forces, explain why the boiling point of CS2 is higher than that of COS. The College Board and the AP exam would never ask you to predict which of these molecules has a higher boiling point. That would be an unfair question because you might pick the COS because it's polar. But if you're given data, you absolutely must use the data. So here is a list of all of the misconceptions and errors that students made on this particular question. Okay, students failed to identify the IMFs in both molecules. They just talked about London dispersion forces in CS2 and did not mention anything about COS or vice versa. Some talked about the fact that the CS bond is polar and that's why it has a higher boiling point. But in fact, they forgot to mention that the two bond dipoles within the molecule actually cancel each other out. So saying that CS bonds are polar is not helping explain why this molecule has stronger attractive forces. The molecule overall is not polar. Some students said CS2 has stronger intermolecular forces and then just stopped there. They didn't actually identify specifically the London dispersion forces in CS2 are greater than the combined LDFs and dipole-dipole forces in COS. And then some students reversed the explanation because they were confusing boiling point with vapor pressure. So they thought that 319 was a higher vapor pressure and somehow had weaker forces. Some students said that the CS2 and the COS only have LDFs. That's incorrect because COS also has dipole-dipole forces. Some students said that both molecules have both LDFs and dipole-dipole forces. That's incorrect because CS2 is non-polar. And of course, that misconception that I mentioned earlier, some either implied or stated explicitly that boiling a liquid is breaking up the covalent bonds within the molecule. Some talked about molar mass and that CS2 is heavier. That's not a good explanation. And some, even though they had the data staring them in the face, they still managed to say that dipole-dipole forces are always stronger than LDFs. So this is the official answer. The scoring guidelines talk about the fact that you mention the intermolecular forces in each molecule, and you say that the LDFs in CS2 are stronger than the combination of LDFs and dipole-dipole forces in COS because that's what the data tells us. All right, so today we talked about polarity, intermolecular forces, and properties of liquids and solids. Now to your homework question. There are 3 screens. I'm not going to read these questions out loud. This is from the 2012 AP Chemistry exam. Here is screen number 1. Here is screen number 2. And here is screen number 3. So that's your homework for Monday's class. Mr. Byrne will explain these answers at the top of his lesson on Monday. Remember about the helpful chemistry resources in the link in the video description. This has been Michael Faribaugh from Albemarle High School in Charlottesville, Virginia. Thank you very much for watching. And again, go to cb.org/tech if you or anyone you know has needs for mobile tools or connectivity for the AP Chemistry exam this year. Thanks for watching.